Okay, so this video is another lecture on Math 1133, Calculus for Business. We're going to be talking about applications of linear functions, reviewing some algebra in Chapter 3. So the first example I want to talk about is basically a way to use linear functions to model cost, revenue, and profit. So let's say that we have a function that we're already given. Right? Let's say that the cost in dollars, let's say in US dollars, cost in US dollars to produce some widget. I don't know. Let's say these are some sort of microchip for a computer device, right? So let's just say integrated circuit, some sort of integrated circuit, right? And let's say it's given by C of X equals, let's say 2.5x plus let's say 150,000. Okay. And we're gonna look at what does this function tell us? What are the two numbers? Basically, what does 2.5 mean? What does 150,000 mean? So the 150,000, this is called the fixed cost. This is the costs that have to be paid just to get started, regardless of how many integrated circuits you make. So this is probably, depending on what kind of integrated circuits you're making, if you have some sort of printing process, it's a really simple thing and they're just printed out. Well, you're either setting up the equipment to do the printing, you are paying someone to run the machine, to set up, to do maintenance. Maybe it has to be serviced every morning. It has to be checked that the machine is working correctly. And how many you make that day has nothing to do with what it costs to set up the machine and do, systems check and make sure it's working, right? There'd be lots of things, whatever the fixed costs are. The 2.5, this is called the marginal cost. What this represents is, what are the costs per integrated circuit? This might be materials costs. This might be related to, well, you have to have someone run the machine while it's going. And the more you make, the more time it takes. So the longer that person has to stand there or sit there or whatever and, run the process or just keep an eye on it, make sure nothing goes wrong, right? So the fixed cost would be setup associated, for example, and marginal cost could be materials costs and then labor costs, skilled labor in this case. So then we can look at, well, what would be the cost of producing 1,000 of these things? And I didn't write this out, but X is the number of integrated circuits. Okay, so what's the cost to produce 1,000? Question mark. Well, you would plug 1,000 into the function. So C of 1,000, that would be 2.5 times 1,000 plus 150,000. So 2.5 times 1,000, that's 2,500. So this would be, what, that 152,500? So, the variable cost, the marginal cost times the number that you're producing, the variable cost isn't that much. Most of the cost producing a batch of that size, almost all of it really, is coming from the setup cost. So you're not really being very efficient. What about if you made 10,000? So that'd be C of 10,000. So 2.5 times 10,000 plus 150,000. Well, that's going to be 25,000 plus 150,000. So that's going to be 175,000. So now you're doing a little bit better. Your variable costs are 25,000, your setup costs are 150,000. And it might be that 10,000 is all you can sell, and you just price accordingly and you make your profit. It's okay if your setup costs are most of the cost. That's fine. It's just maybe not so efficient. what if we were going to make 100,000? Like if we were able to sell 100,000, basically what's going to happen is something, well, I don't want to get ahead of myself. We'll examine that looking at average cost in a minute. What is happening when I say we weren't being efficient? What do I mean by that? We'll get to that in a minute. So if we make 100,000, well, that's going to be 2.5 times 100,000 plus 150,000. 150,000. Well, so that's going to be 250,000 plus 100,000. So that's going to be 400,000. And at this stage, most of my costs are due to the variable cost. The materials and the skilled labor are making up the bulk of the overall costs. So if I were just going to do this, I have a lot of overhead. The vast majority of my costs are from equipment and setup, stuff like that. Here, I'm being a little more effective with my results, I guess, where, per unit is the per unit cost is really the driving factor in the total cost. Okay. Basically, what would be required up here is I'm not spreading out my cost very much, my fixed costs. So I'm going to have to price things really high to make up for it. I'm only selling 1,000 of these things, right? Let's look at what would be the average cost to make 1,000 of them. Well, when you do an average, you take the total and divide by how many things you're talking about. Like if you're averaging grades, you add them all up, divide by the number of grades. So if you've got, I don't know, 10 homework grades and you want to know what's the average, well, you add them up, divide by 10, right? So C bar of 100, or sorry, 1,000. This is the notation that represents the average cost, and it's defined by C of 1,000 divided by 1,000. Okay, so this is going to be 152,500 divided by 1,000. That's 152.50. Okay, so it costs $152.50 on average to make each one of them. That's basically how spread out are the costs. The materials was only $2.50, but the total cost to produce is $152.50. So the vast majority of the costs are from the fixed cost. If I make 10,000, what would the average be? Well, C bar of 10,000, that's going to be C of 10,000 divided by 10,000. That's going to be 175,000 over 10,000, which is 1750. Oops. Pretty sure that's right. Yeah, 1750. So the average cost per unit came way, way down because I'm making more of them and I'm spreading out that fixed cost. So when I go to price these things, if I was only making 1,000 of them, if I want to make a profit, I'm gonna have to charge like it. If I want to make a small profit, I'm gonna have to like charge $155 each to barely make anything. And really, I might want to charge like $200 each or $250 each or something like that, right? In order to make it reasonable profit. Here, if I'm making 10,000 because I'm spreading out those fixed costs, charge $20 if I want to just make a small profit. Charge $30 if I want to make a big profit because I'm making more of them, and my materials costs are so low. Making more is a good idea. For me, so it's easier to turn a profit. But that hinges upon being able to sell 10,000 of them. What if I make 100,000? C bar of 100,000. So this is going to be C of 100,000 divided by 100,000. So this is going to be 400,000 over 100,000. So $4 each. It's super cheap at this point. And if you think about it, as I make more and more and more of them, if I make 1 million or 10 million or whatever, the average cost gets closer and closer to whatever that materials marginal cost was, right? If you make enough of them, the fixed costs stop becoming important because you're making so many, making such large volume that setup cost doesn't matter that much anymore. Um, so that's just some questions we could ask about a cost function. If we're given a function, and in particular, this is a linear function. Let me back up a little bit and point out that I said this number right here is the marginal cost. Well, that's because I have a linear cost function. If my cost function were quadratic or cubic or exponential or whatever, then the marginal is more complicated. Basically, the marginal, and this will come up again later, this is the slope of the cost function. Okay? And when you have a curved graph, slope is not nearly as simple as it is for a straight line graph. Rise over run is relatively easy. And the point of doing calculus is, well, what's the marginal? What's the slope when your function's not a straight line? What about if it's curved? Okay. The next thing I want to do is look at just another application of something you can do with a linear function. So if you're not given a linear function, but you're asked to set one up. So there's this general idea of depreciation. Goods depreciate in value over time, especially durable goods. They retain value over time, but it degrades over time. So if you buy a car, you drive a new car off the lot, it's now not worth as much as it was. It cannot be sold as new anymore, right? It loses some of its value in the course of the couple of seconds it takes to drive off the lot. And then, some vehicles will lose value quickly, some will lose slowly. And I did a little bit of research. What if I went and bought a new Honda R-Type? So if I went and got a 2020 Honda R-Type, specifically the Honda Civic R-Type, or Type R, I forget right now. And I was looking at their website, and if I got the one I wanted, that would be $42,260 be the sticker price. And another website was saying that from their research, this particular model, not the 2020, but recent Civic R-Types, they retain a certain percentage of their value. So let's say that this is new. This is the sticker price when I buy it today. And my estimate, based on the little bit of research I did, would be that 3 years later, that the value would be about 36.7. Okay, so if I assume that the depreciation, the value is consistent over time, that it loses the same amount of value every year, right? How can I represent this with a formula where I can say, okay, what's the value after 4 years, 5 years, 6 years? Now, of course, you could do this just with arithmetic, but we want to gain some familiarity with functions. So I'm going to build a linear function that models this information, and I want to know two things. I want to know, okay, what's the value at 7 years? Okay, because that's when the extended warranty runs out, so I kind of want to know that. I might want to get a new one at that point. And then we could even ask, when is the value? When is it hit, or when is it less than, say, I don't know, 21,000, half the value? And maybe these are actually the same question. I haven't worked this out ahead of time, so we'll see how it goes. Well, what I can do is say, well, this new, if I say this, that I'm going to make the value as a function of time, okay, v of t, function of time. So it's going to be some slope times the time. And do I want to use x? Let's use x. Instead of t for time, we'll use x. That's fine. V of x equals mx plus b. That's, the slope intercept form for a line. Now I know, okay, well, what formula is that? Well, there's a couple ways to do this. I could say, well, this information, that when it's new, the value is 42,260. I can say, okay, well, that means that the ordered pair 0, 42,260, that is a point on the graph of that function, right? When x is 0, meaning 0 years, I just got it, the output, the value is 42,260. And then 3 years later, when x is 3, it's 36,7. And I know it might look a little confusing because I'm using commas for two things. So maybe I should get rid of these commas just because I don't want it to be confusing. Okay. Well, what I can do is say, well, what's the slope between those 2 points? I can do rise over run. Okay, I could do the second value minus the first value over the second time period, or not time period, but time, minus the first time. Okay, and here the value is playing the role of the y variable because the outcome is a value, the dollar amount. So I'm using v for value. Well, that will be 36. That's the second value at the end of 3 years minus 42,260. That's the initial value over 3 minus 0, the number of years. What I'm kind of doing is I'm doing the average change in value over the 3-year period. The value goes from 42,260 down to 36,7 over a 3-year period. And so I'm taking the total change in the value and dividing by the number of years to get, well, what's the change per year? So I'm kind of doing an average, a little bit like the weighted average up there. Take the total amount you want to ask about and divide by how many time periods or how many items, how many somethings. So it's how much over how many, basically. So what is that going to be? Let me grab a calculator. So 36,7 minus 42,260. So I get negative 55,60 all over 30. And that doesn't divide evenly. So I'll go ahead and get a decimal value just to have an idea of how much that is. Although when I write out the function, I'm going to keep the fraction, but I would like to know, well, roughly how much is that? So this is about negative 1853 and change. I'll keep 3 places, okay? But it would be repeating decimal, but I'm indicating I'm rounding so that I don't need to write like the rep 10 bar or anything like that. Okay, so that, what I'm finding when I do the rise over run, I'm finding the slope. What is the change per year? And now I just need, well, what is the y-intercept? Well, the y-intercept on a linear, the graph of a linear function is the value when the input is 0, right? If you have, I'm going to try to do a sketch of a graph. I'm not going to try to be super accurate. I just want to have a rough representation. If you have some linear graph, then this value right here, the y-intercept, is what is the output value when the input value is 0. Oh, but that's the initial value we're given. So that y-intercept is 42,260. So my function is going to be v of x equals negative 5560, because I just don't want to use decimals here. I don't want to round anything yet. Over 3 times x plus 42,260. And if I plug in 0 into this function, well, then I'll have that fraction times 0, which would be 0 plus 42,260, and that's matches this data point. If I plug in 3 for x, right? Let me change colors here. If I plug in 3 for x, I'm pretty confident that I would end up getting as the total for this expression 36,7. Okay, and you can check that for yourself if you want to. But I'm asking, well, what's the value at 7 years? Since what I've come up with is called a linear value depreciation function, I'm assuming the same loss year to year. I can plug 7 in and say, well, approximately, what would be the value at 7 years? So v of 7 is negative 5560 over 3 times 7 plus 42,260. I can throw that whole thing in the calculator. Negative 5560 divided by 3 times 7 plus 42,260. I'm looking at 29,286.666, repeating, right? Well, 67 then if I'm rounding, right? So after 7 years, it's still worth almost 30,000. Hey, that's pretty good. The website I was reading, the article is pretty optimistic that the R-type would hold value really well. Okay, so then I could ask, well, when is the value less than 21,000? Well, I could say, okay, well, when is v of x less than 21,000? Well, just plug my linear function in there. Oops, got that backwards. And I'm just solving an inequality. Okay, so I'll subtract 42,260 on both sides. So negative 5560 over 3. X is less, and I'm confident in doing this mentally just because 42 is 2 times 21. So negative 21,260 if I subtract 42,260 on both sides. I got lucky there. I didn't choose this number intentionally to make it easy, but I got lucky. So then I can multiply both sides by 3, and I'm running out of room here, but that's okay. So negative 5560 is less than, if I multiply by 3 on both sides, that's going to be minus 63,780. And then I need to divide by negative 5560 on both sides. When you divide an inequality by a negative, you switch the order of the inequality. So x greater than negative 63,780 over negative 5560. And that is kind of a messy number. I guess I can cancel out the minuses and cancel out a 0 on top and bottom. And while those are both even numbers, I'm just going to throw in a calculator. I'm not going to try to reduce that mentally, and I'm not even sure that it would. So we get about 11.47. So that means roughly 11 and a half years. So after 11 and a half years, it's going to still be worth 21,000. So that's pretty good. And this is sort of coincidental. I didn't really plan this out, but this is roughly half the original value. I mean, I could have just said, when is it at half value and done 21,130, but I didn't think of that when I wrote the problem out. So after 11 and a half years, it still has about half its value. So the car will be, if this prediction is accurate, we're assuming a whole lot. We're assuming that there's linear depreciation, and every year the same amount of value is lost, right? And also the article I read was kind of optimistic about holding value. So anyway, so that's just an example of one thing that a linear function can be used for. You can use it to make predictions about future values, but you do have to assume that the thing you're modeling with the linear function behaves a certain way. And you might remember in this review of some algebra stuff, we're primarily reviewing linear and quadratic functions, functions specifically linear and quadratic. From algebra, you're probably familiar with other kinds: cubic, polynomial, rational, exponential, logarithmic. We're not going to review every kind of function. As we go along in the course, we can spend some time reviewing as we needed, but we're just doing linear and quadratic specifically in these initial lectures. So what's the next thing? So I want to get to two types of application problems, but before we do that, we need to talk about a general concept. How do you find when two functions agree? Or in other words, where do the graphs intersect? Where two functions agree / intersect. Let's put it that way. Okay, and since we haven't gotten to quadratics yet, we'll do just linear functions. So if I had my XY axis, something like that. And I have a linear function like this and a linear function like this, right? And I'm not going to put arrows on these, but these are lines. I could ask, okay, what is this x coordinate where they agree? And I can ask, okay, what is the y coordinate where they agree, right? So let's say like this is f of x and this is g of x. Where does that occur, right? And there's different ways to approach this. One way, and let's just do an example of that, is say, well, if f of x equals, say, I don't know, this is sloped downward, so I'll use a negative slope. Let's say this is like 8 minus 1/2 x. Okay, and then g, this is sloped upward, so use positive slope. Let's say this is 2x plus 4, something like that, right? We can ask, when do these two functions, for what input do these two functions have the same output? When do the graphs intersect, right? One way to do that is to say, well, if the two graphs intersect, then there's some number f of, and I'm using question mark in 2 places, so let's get rid of this one for now. F of question mark equals g of question mark. There's some value to where the two functions have the same result. Well, all I got to do is take these two formulas and set them equal to each other and solve the resulting equation, and that will give me, here's the x value, where the outputs are the same. So let's do that. So 8 minus 1/2 x equals 2x plus 4, and I just want to solve this linear equation, which might not be very hard. There's a fraction involved, makes it a little bit harder. What I generally like to do when I have fractions in an equation like this is to get rid of the fractions as my first step. So I'm going to double everything, just because I don't want to deal with fractions if I can avoid it. So I'll have 16. My numbers get larger, but there's no fraction. 16 minus x, 4x plus 8. Okay. Next, I'm going to get x on one side only, because this is a linear equation. We just want to get x by itself, so I'll add x on both sides. So I have 16 equals 5x plus 8. Then I want to get that 8 to the other side, so I'll subtract 8 on both sides. So 8 equals 5x. And then I want x by itself. That's my overall goal here, so I'll divide both sides by 5. Okay, so 8 fifths, that means this is the x coordinate where the two functions agree, okay? They have the same output. So anytime you want to know, well, where do these two functions agree? Just do this. That'll work fine, okay? So what can we apply this to? The first thing is the idea of break-even analysis. If you have a cost function and a revenue function for some business, how do you work out how do they, what would be the break-even point? How many widgets do they have to sell? Or how many memberships do they have to have, or whatever, in order to break even? So let's say that for some widget, I don't know, not an integrated circuit, not a car, just some widget, which I'll usually say widget just because it's a generic thing. Let's say that the revenue is a function of the number of widgets. Say R of X, let's say it's 75X, okay? Let's say the cost to produce these widgets is like 8X plus 12, right? Well, let's not say 12. Let's say 1,200, okay? We could ask how many widgets, if they cost 75 a pop, I'm sorry, if you sell them, rather, for 75 a pop, your revenue is the price per unit times the number of units. So 75 times X, that's because it costs 75 each when you sell them. The sale price, not the price to make them, of course, not the cost to make them, is 75. And then the marginal cost is 8 and the fixed cost is 1,200. Well, how many should you make to break even? And then, of course, you would make more than that to turn a profit, right? Well, all we got to do is say, well, where are these equal? So we want to say, well, when is the revenue equal to the cost, right? So 75x equals 8x plus 1,200, okay? So it's kind of like this. It's just a linear equation since we have linear functions. So I'll subtract 8x on both sides. So 67x equals 1,200, and I can divide 67 on both sides. So x is 1200 over 67. Well, that's a messy number. I want something a little more recognizable, so I'll throw this in a calculator. Again, I just made up these numbers. I didn't choose numbers that work out to get a whole number result. So I get 17.91. Well, that pretty much means, you interpretation or conclusion, how many widgets? 18 widgets. That will let you break even, okay? And it doesn't take that many because the sale price is so much higher than the per unit cost, the marginal cost. So it doesn't take that many to overcome the um, fixed costs. And of course, you wouldn't just stop at 18. You'd say, well, let me sell as many as I can. I need to sell 18 to break even, and then I'll sell more if I'm able to. So that's the basic concept. Look for where are the two functions equal to find out where you break even. There is a little bit more to that. When you ask, okay, so 19 would be a profit, right? 20 widgets would give you a profit, right? If you want to check that, you'd say, well, what's my profit function? My profit function, this is going to be my revenue function minus my cost function. So this is 75x minus 8x minus 1200. Okay, so this is 67x. Oh, in parentheses, it's still plus. Sorry about that. It's going to become minus. So 67x because I have 75x minus 8x. And then this minus also applies to the 1200. So minus 1200. So here's my revenue function. So I could then check, or sorry, profit function. So I could then check, well, if I plug in 18, do I get positive profit? If I plug in 19, do I get positive profit? And indeed you would, but something you could check for. And when we go to do later problems where our functions are not linear, it becomes important to check. Just finding the break-even point, finding this doesn't tell you, well, wait, do I profit with 17 or do I profit with 18? Because the break-even is 17.91, on paper. But is which side of that? Do I make less or do I make more of them to turn a profit? Well, you would imagine it's generally more, but depending on the functions, not necessarily. It would be possible that if you made too many and you couldn't sell them all, well, you're not getting revenue on those ones you didn't sell. So if you could make so many that you lose money if you're not able to sell all of them. And that's a more complicated thing that we'll get to in later examples. So that's pretty much that example. Just how do you find a break-even point? It's an application of linear functions. So the next thing is supply and demand, which you may be familiar with with this, especially if you have taken an economics course that covers that. And typically in a first year economics course or first semester economics course, all the functions that they deal with will be linear because it's just the algebra is easier. The geometry of it is easier. Later in this course, we'll deal with supply and demand functions that are not linear. And so we're just sort of setting the stage here. You understand how to deal with them so that when we get to the applications using calculus, you'll understand the beginnings of those. You'll already get how to find the what we're going to call the equilibrium. So just a basic overview. And again, this may be something you've seen before. When you have supply and demand curves, they basically are functions that relate how consumers value an item and how producers value an item. So if our horizontal is quantity, our vertical is price. Okay. So the horizontal axis is the number that are going to be produced or sold or purchased, and then the vertical is the price at which those things occur. So demand curve generally will be a decreasing function because as the price comes down, more people want it, whatever the item is, right? And struggling with the interface here. Sometimes the interface is a little weird. So generally you have a decreasing demand function. Let's say that's our demand, right? And then generally you have an increasing supply function. As the going rate, the going price goes up, more producers go, oh, well, we want to make that and we want to make the profit rather than someone else. So this point where those two graphs intersect, this is called the equilibrium point. And, in economic theory, you make a bunch of assumptions about how people behave. They behave rationally when they have complete information. You have to make some assumptions to do this, to mathify it, especially. So this is theoretically what would occur. Like, this is where the price would settle. The consumers know everything they need to know about the product, and they assess its value appropriately. So right here, this horizontal coordinate, this is the equilibrium quantity. So I'll represent it as Q with the subscript E. This is the quantity that will be made and sold once things sort of settle out. And then this right here, struggling with the interface a little bit. This is the equilibrium price. Okay, this is the going rate, the price at which, the level at which the price will settle after, given that consumers know what things are worth, they know how much money they have, producers know that their capacities, things like that. So for a given supply and demand curve, what's the equilibrium quantity, right? That's something that we'll need to be able to find. So let's say that the supply curve, S is a function of Q. This is the upward sloping one, because supply will always, the price at which the product is supplied will always go up when the quantity goes up. More demand, the producer wants more money for it. So let's say this is 0.4 Q plus 3. Okay, and let's not worry about what these numbers represent for now. So D of Q, this is going to be the demand curve, which will be downward sloping, because as the price comes down, more people want the product. Well, not that more people want the product, but that they decide that the cost versus value becomes worth it. You're charging $50 for that item. I don't really want it for $50. It's not worth that much to me. Oh, the price is $35. Now I will buy it because now it's worth it to me. Oh, the price is $25. Well, I'll buy 2 of them at that price. That kind of thing. So let's say that this is negative 1.2 Q plus 10. That's the demand curve. So we could ask, given that supply curve and that demand curve, what's the equilibrium? What is the quantity that will actually be produced and sold? Well, all I need to do is set these two things equal to each other and solve. I'm finding the quantity at which supply and demand agree on the price. When do the consumers and producers agree? Yeah, that's the price we should have, so that the most people are happy with it and the most commerce actually occurs. So 0.4 Q plus 3 equals negative 1.2 Q plus 10. Okay, and I want to solve for Q, so I'm going to add 1.2 Q to both sides. So I get 1.6 Q plus 3 equals 10. And then I'm going to subtract 3 on both sides. So 1.6 Q equals 7. So then I'm going to divide both sides by 1.6. So Q equals 7 over 1.6. 1.6 is also, I believe, 8/5, but we'll just use a calculator to work this out. 7 divided by 1.6, I get 4.375. Now I'm not rounding, this is the exact value. 4.375. So that is the equilibrium quantity. Okay, that is the quantity. Quantity value at which the supply and demand both agree. Okay. And then I could ask, well, okay, great. What's the equilibrium price? Well, what I need to do in that case is I want to know what is this height level on those graphs. I can take this quantity and throw it into either of those functions. It doesn't matter which one because they agree. So just pick one. I'll go with supply. So I can say, okay, what is S of 4.375? Okay, so that's going to be 0.4 times 4.375 plus 3. And I'll throw that in a calculator. And I believe I'm not going to have to do any rounding. I'm just going to get an exact value from the calculator. I get 4.75. There we go. That is the equilibrium price. Okay. So that's just 2 applications of linear functions. What can we do with these linear functions? And that's pretty much it for this section. This video is a little bit shorter than the previous one, I think, by a little bit. So in the next section, we will look at quadratic functions and applications of quadratic functions, and after that, we'll get into actual calculus. So I'm going to go ahead and end the video there.